So I would first like to give you a motivation, what led us to think about embedding theories. We didn't start by saying, okay, we wanted to develop a quantum embedding theory because just like that, but we were motivated by specific problems, and I would like to describe these problems quickly and to put the development of the quantum embedding theory that I will then present within the perspective of a general electronic structure framework of methods. Also, because since we are here for a while, it would be good if anybody wants to discuss not only this, but also the other method that we are developing in the group. And then the quantum embedding theory led us to define an effective Hamiltonian and then to do calculation also on quantum computers. And I want to tell you a little bit about that. So there will be a quick first part, a central part, and then the last part on quantum calculation. So our interest in quantum embedding came from our interest in basically designing materials for quantum information technologies. And in collaboration with the experimentalists at the University of Chicago, we focus on a very specific system. This is a semiconductor, actually with a quite large gap. And we want to have two-level system created by defects, by having defects in this system, and for a number of applications. I will not talk about application today, but depending on the energy differences and on the gap of the system, you can think about application in communication, even computing, and especially sensing. And we want to know the electronic structure of the system because we want to optically address this system to store information. And so we want to have optical transition from the ground to unexcited states that we are able to describe, followed by a spin-selective decay path with non-radiative transition between states of different spin multiplicity. And then we want to be able to describe photoluminescence between different states, right? And this is one example that sometimes is referred to as the hydrogen atom of spin qubit. It's the nitrogen vacancy in diamond, and it has been studied for many years by many people. So, at the end of the day, the other thing that you really want to understand are coherence properties of this system, although I won't talk about this today. I just want to let you know that we did quite a bit of work also in this field in recent years, and if you're interested, of course, I'm interested to talk to you. So defects in a solid, we need to understand, is it stable? What's the atomistic structure? Sometimes you don't know from experiment what exactly the atomistic structure of your system is. Coherence time, and here we will focus on electronic structure in a minute, but let me put it in the context of what we do, right? So first of all, we have a defect. For example, this is something that we have studied a lot, a double vacancy in silicon carbide, and we want to understand the electronic properties, so orbital energies or charge state. And what we do to start with, we do density functional theory calculation. You could also use quantum chemistry method. Sometimes you don't know how the defect is formed, and also sometimes you don't know the exact structure of the defect. As simple as this little thing can be, this we know, but sometimes we don't know from experiment. And so if you want to understand how this thing is formed, and this is something that we have done only for one system, you may want to couple your first principle calculation with advanced sampling techniques to do dynamical simulation to understand free energy surfaces of the defects. Okay, so here is the central part of this talk. You do start by doing density functional theory calculation and looking at orbital energies, but it turns out, and this was our motivation to develop quantum embedding, it turns out that some states are multi-reference, some states of these defects. They cannot be described by a mean field theory, and there is no way that you can either interpret experiment or predict anything from experiment if you are not able to understand what we call correlated neutral excitations. And this is why this was started by my student, Ma He, when he was in my group. He's now working at Google, looking at a region of the system where we can define an active space and then do a quantum embedding. I'll get this in a minute. When you have the electronic state of your system, of course, you want to do the optical properties. I told you that one property that is very important is photoluminescence. And we have developed techniques to study photoluminescence. So, this little thing here that you cannot see very well is actually a comparison between computed and measured photoluminescence spectra as a function of temperature. Not to say that we can do this for any system we want, but for some system like silicon carbide, we can, and we can get a good agreement. And finally, and we do this by doing either constrained DFT or time-dependent DFT as of recently, for which we also have developed analytical forces. So finally, once you have a handle on your electronic structure, you understand your photoluminescence property, you can compute spin and coherence properties. And we do this by doing spin Hamiltonian with ab initio parameters. And so I told you this story for a defect in a solid. However, these are very general framework that you can, and when you couple these quantum mechanical method, that you can do also for molecular qubits. And this is a molecular qubits that we have studied very recently in collaboration with David Ashelom and Dana Friedman, and for which we have computed actually spin and coherence properties, and a paper will go out soon about that. Okay, so now we focus on this part, and I would like to tell you what we did by doing quantum embedding calculation. And also, given the audience and given the workshop, I would like to point out to you what the problems are. There are a number of open problems, and I would like to point out what the open problems are. But it is perhaps good to keep in mind what is this quantum embedding that we are doing, what is the general framework. Okay. So this is what we have done in a nutshell, and then I would like to go a little bit more in detail. So we do a first principle calculation based on DFT, and that can be semi-local functional or a hybrid functional, and then we identify an active space of orbitals. I'll tell you in a minute how we do that using a localization function. And this is the active space composed by the state of the defect, right? And then we ask the question, can we actually compute the effect of the environment on this active space in such a way that we can define an effective Hamiltonian that represent the states of my defects in the field of the environment? First of all, this is not a new idea, okay? This question of having an active space and then having something that tells you the effect of the environment, people have thought about this before. So what we have been able to do is to find a way to compute the effect of the environment on the active space by computing a so-called screened Coulomb interaction, which takes into account the correlation between the electrons, in a way that does not involve the calculation of any virtual electronic states. And this comes from the work that we have done over the years to try to make GW and Bethe-Salpeter calculation more efficient by looking at using a spectral decomposition of the dielectric matrix. So the dielectric matrix, gives you the connection between the bare Coulomb interaction and the screen Coulomb interaction, right? So we go by the picture proposed by Hedin, in which we solve an approximate form of the Dyson equation that contains the screen Coulomb interaction. Lots of words here, but so the point is we describe the environment at a level of many-body perturbation theory. We compute the screening without computing empty states. And we can also couple the calculation of the screening with done with two codes by doing the calculation not with the many-body not with perturbation theory, but in finite field. Why do we want to do that? Because in this way, we can we can do calculation easily with hybrid functionals. Okay, so let me summarize. We identify an active space. We do a calculation that is based on methods that we have developed without empty states to do GW calculation that give us the screened Coulomb interaction of the environment. And by doing this, because we do not need to compute many empty states, we can scale our calculation to solids with hundreds of atoms. So the hundreds of atoms are the environment, okay? Defects, very small number of atoms. And then we have our effective Hamiltonian. Yes, please.
So in these calculations, is there one active region or there are multiple active regions coupled together?
There is, there is one active region, but you need to be careful about the fact that these are calculations in periodic boundary conditions. So you always need to be careful that there is no interaction between a different region. I mean, the whole framework doesn't, you could have different defects in your system, right? You don't have to have only one defect. We have not done this, although, of course, although it's scalable to many hundreds of atoms and so on and so forth, there are still limitations. You cannot do everything, you cannot do 5,000 atoms, you can do up to 500, 700 atoms, just to give you an idea, with four electrons per atom. Okay, so now, as everybody else who has ever done embedding theory, we have a problem. And the problem is a problem of double counting, okay? So we have an environment that we describe at a low level of theory, things G0, W0, and then we have an active space that we want to be able to describe at a higher level of theory. And we have, this is super technical, but it's also super important. So I want to point this out, and I will not describe the technical part, but I will be very happy to discuss this. So there is a double counting terms that you compute twice when you do the calculation for the environment and for the active region. You need to be careful to remove it. Okay, so at the beginning, meaning in the first paper that we published, and this is a lot of matrix elements, and again, there are 2 papers explaining this in details, and we can sit down and look at the papers. But in the first inception of our quantum embedding, we used the double counting that was based on Hartree-Fock. So we just removed the exchange part of the calculations. And this was based also on what other people had done in similar environment. And then we realized that this was not the best thing to do because there were some errors. And then, Nansheng and Christian Forwerk, who are the first author of this paper that we just put on the archive, worked out what we call an exact double counting. So let me explain what the word exact means, okay? Because there is never anything really completely exact. So if you describe the environment at the G0, W0 level of theory, okay, if you have a G0, W0 level of theory for the environment, then you can show by doing a diagrammatic expansion that you derive an exact expression for your double counting. You can exactly remove it. It's fully consistent with the choice of G0, W0 at DFT, and there are no errors introduced. And so we corrected some of the, it was not bad, but it was inaccurate that we had before. And now I tell you what we do. So basically, this is the deal. So we do a calculation by doing a calculation, a DFT calculation. either quantum espresso or with QBox, especially if we want to go beyond RPA and have a calculation in finite fields that QBox does very efficiently. We define a localization function to pick the states that are part of the active space. We construct our effective Hamiltonian from the orbitals that are in the active space. Or I should say, to describe the orbitals that are in the active space. And then we diagonalize it. We diagonalize it by doing full configuration interaction on a classical computer or by running the Hamiltonian on a quantum computer. And so now I will tell you first, and the diagonalization is done. So there is, all those codes are now coupled, and diagonalization is done in PySCF, which is not something that we have done, but that we have used, of course.
Sorry, another quick question. So double counting is frequency dependent?
No.
There is a G naught, W naught.
No, so
like the G naught, W naught, so those. They don't depend on frequency?
So this, the frequency depend, no, it does not depend on frequency. We can discuss the problem of, yeah.
One more question. But still one cannot, there will be a term coming from the functional that one cannot decouple the exchange and correlation, which will go through G0, W0, which will cause that additional double counting due to non-self-consistent nature of G0, W0.
So I'm not sure I understood correct. I mean, I've heard correctly what you, can you say it again, just shouting a little bit?
All right, so if one would do exact GW, fully self-consistent,
yes.
then one could remove fully the double counting because the starting point from DFT would be fully eliminated. If one only does first iteration, even if one does the diagrammatics correctly, there is still some double counting left because of the inability to basically remove the double counting from the DFT part and counting the tiny bit of correlation because G0, W0 still depends on the starting point.
So I'm not completely sure, I mean, that I fully understand what you're saying. But so first of all, I will show you results where there is a very little dependence on the starting point and on the DFT starting point. But your question is different because your question is analytically the fact that, I'm not sure if I fully understand it, but if you look at this, and we can look at this paper and all the derivation together, this double counting is actually exact when we when we do the diagrammatic expansion, and it does not depend on XC, VXC. That's, I don't know, Marco, do you have anything to add?
So the W naught is a first order perturbation, so there may be some dependence on the starting point of DFT.
Well, but of course there may be, but I'll show you two results where there are, with very, very little dependence. That's so. But of course, then one question that you can ask is why don't you do G0W? Why don't you do GW fully self-consistently? And because we haven't done it yet. That's okay. So, so let me show you how the results depend on the choice of the DFT. PBE is one functional, DDH is a hybrid functional where there is a mixture between the mixture fraction for the in the hybrid functional is proportional to the inverse of the dielectric, the long wavelength dielectric constant. And of course, this DDH is explicitly for solids, okay? So, so basically, this is NV minus. So we define a localization factor here to pick the orbitals. We define the active space depending on the threshold of this localization function. And we look at the convergence of the results here. And this is the convergence of the different states. These are labeled according to the group of the defects, and this is how our results converge as a function of the chosen threshold, and these are converged results. So I have to tell you one thing that I'm not showing here, which is there is a convergence that we have to check every time in terms of the number of eigenpotential that we include in the spectral decomposition of the dielectric matrix, okay? So there is no calculation of unoccupied states, but there is a convergence to be done in terms of how well you represent your dielectric matrix, which I am not showing here. And we need to be very careful because for these cases that I'm showing here, NV minus in diamond, and also the next case, this interdependency of convergence is simple. We have it completely under control. If you go to oxides, that I'm not showing here today because we are not done with that, the interdependence is not that simple. And annoyingly, absolutely not that simple. But anyway, see, beautiful convergence for this case. And if we look now at the results, these are, you can see here, just compare the two red results. One is starting from PBE and the other is starting from DDH. And you see the dependence is not, it has not completely disappeared, but it is not very big, and it's completely under control. And of course, before, when we had a different type of double counting, we had a different type of dependency. And for one number that these electron volt that we can compare with experiment, the result seems to be reasonable, although the measurement of the experiment is not exactly what we are computing. There is, anyway, the comparison seems to be reasonable. Now, let me tell you another case where there are a number of things that yet needs to be understood.
You get also lifetimes somehow?
We haven't, but in principle, in order to get lifetime, you need to do some more work, but this could be done. So let me tell you this about this case. This is a very interesting, it's a silicon vacancy neutral in diamond. It is very interesting for many reasons that I will not go into for experimentalists. And here we have a series of problems, okay? So these are calculations done by my colleague Laura Gagliardi in Chicago. This is this paper here, done with another different type of embedding. And, we don't fully agree. And we don't fully know why, okay? So again, the dependence on if you look at the dependence on the starting point is small. And small always means depending on what you're interested in. These are electron volts, so it's not zero, okay? So there are, you could say the first eigenvalue is not too different. The last eigenvalue actually is in pretty good agreement. But then there is this intermediate one, and we have rationalized the disagreement with experiment, both for us and for what has been presented in this green reference here, by the fact that the experiment measures ZPL, zero phonon line. So there is a relaxation that we are not accounting for. But we don't, honestly, we have written this in our paper, but we don't know if this is completely true. I mean, this is one interpretation, and it could be also done by dynamical Lian-Teller effects that we are not considering here. Okay, so we are not the only one, and certainly not the first one, to do quantum embedding theory for electronic excitations. There have been a lot of work based on embedding, based on the density, based on the density metrics, and I called the theory that I just presented here, or I should say not the theory, but the framework, quantum defect embedding. This is within a Green's function formulation here that include the quantum embedding that I think that Dominika will talk about, and also include the MFT. So here I've tried to highlight at a very, very general level what are kind of the differences and the different kind of applications. So if you look at the dynamical mean field theory, and those, there are several versions of dynamical mean field theory. Basically, it is used and applied for total energy and charge excitation. And what we are doing here, we are computing correlated neutral excitations. And if you look at the theory that, again, I think will, oh my God, did I forget your reference, Dominika? This is really bad. No, it's here. Okay, all right. So the self-energy embedding theory. So basically, this also reflects what is the difference in the soul of chemists and physicists, right? So physicists, especially those who work based on GW calculation and many-body perturbation theory, use a screened Coulomb interaction, and chemists always start from bare Coulomb interaction. Since there are so many people here working on this, and I think that it would be really, really interesting to compare different methods, to see what they can do, and to see which kind of system they can work best for. So I put this out there as maybe a beginning of discussion. And here we are trying to publish a paper that really it turned out to be very difficult to publish, where we compare different quantum embedding theory. And I would be also very happy to discuss what we think about the comparison. Okay, so now, now I want to tell you what we have done on quantum computers. So once you have this effective Hamiltonian, you have a Hamiltonian that it's in second quantization. You can run it on a quantum computer. And this is the Hamiltonian that I just talked about. You can use one of the transformations that many people have worked at developing, like Jordan Wigner and other transformation, and that other people have worked at implementing. They are implemented in Qiskit that is maintained by IBM or by Open Fermion. And then you have to choose algorithm to understand how to get the eigenvector and eigenvalues of the qubit Hamiltonian. One problem that you always have, no matter what hardware you choose these days, is noise. Your hardware is noisy. Your results will be noisy. You have to extrapolate them. Or you have to live with them, and you have to understand what is really the error caused by noise. This is hardware noise. Okay, so there have been many calculations. This is just one review paper, and maybe now there are more review papers that are coming out on all the calculation that people have done on molecules on quantum computers. And I would like to point out to you the type of molecules that people can do, right? Just to have an idea of the number of atoms that we are talking about. One of the last papers that came out from Google team is 12, okay? Hydrogen atoms or stuff like that. So these are the kind of molecule that, people are able to do. Sorry, I made a mess. Okay, and these are results. I should have put the exact references, but they are all referenced here, of what people are studying in these days. So these, for example, are potential energy surfaces as a function of distance for molecules like lithium hydride or some other hydrogen molecules. And this here, I will get back to that. These are calculated point, all these colored point here, and then there are points that are noise mitigated. okay? So people are well aware, well before we started doing all of our calculation, of course, that noise is a problem to address if you want to be able to use a quantum computer. So by the way, I should have said, so why would you want to use a quantum computer these days? So first of all, my answer to this is to learn, to understand what the problems are. We are very far from having any hope of quantum advantage yet. There are many, there is a lot of work and there are a lot of controversies whether we will be able to reach quantum advantage for which problems. And so I'm not going to do this, at least in our group and maybe in others, to think, okay, in a couple of months we'll have quantum advantage and we'll beat the FCI. Absolutely not. We want to learn. We want to learn what the problems are and also learn on the way whether there could be some quantum advantage. And there was, there are controversies. There was a talk at the APS given by Garnet Chen that suggested that there may not be for this kind of system. There were other talks suggesting that there may be, so we can discuss this. Okay, so once you have your effective Hamiltonian, you represent it in terms of qubits and quantum gates. And you need to have an ansatz for the many-body wave function. And this is something that we learned the hard way. You have to enforce particle conservation because your Hamiltonian, your qubit Hamiltonian, the Hilbert space of your qubit Hamiltonian and your physical Hamiltonian don't coincide, and you may have states that are absolutely non-physical. We learned this, and maybe other people knew it, but we learned this the hard way by realizing that our VQE, our variational quantum eigensolver, were apparently not variational. And this was due to the fact that we didn't have a particle conservation. Okay, so let me tell you what we do. So when we say that we do a calculation on a quantum computer, the calculation on a quantum computer, it's only the green stuff. All the rest is done on a classical computer. So they are very hybrid, okay? Lots of classical calculation and some quantum calculation. So we do so we start from our DFT, we do our quantum embedding, we do a transformation to a qubit Hamiltonian, we parameterize the many-body wave function, and then we do the calculation with VQE and with the quantum subspace expansion, QSC, for the ground state and for the excited state. So we have a coupling, again, of a number of codes, and then we use Qiskit we use Qiskit. I mean, we take advantage of all the stuff that have already been implemented, and they are available. These are codes that are open source. So they are in GitHub. And then we do our calculations. So the very first calculation we did was 2 years ago, a little bit more 2 years ago. These are just the comparison between classical results, the line, and the results on a quantum simulator. First, you have to convince yourself that you have implemented everything all right, and on your quantum simulator, things are okay. They are. And this is the simplest case that we have done. I will show you some more complex one. And then depending on how you prepare your state and you do your minimization, first of all, good news is you converge. That's already great. Bad news is that there is noise. And so the zero is normalized at zero is the results that you should be getting. And these, depending on the starting point, are the results you get. See here, the difference between the converged quantum on quantum hardware and the classical one is not small. These, again, are electron volt. This is not small. Okay, so recently we tried to use smarter mitigation strategies than we used before. And I will not tell you anything in technically, but point out two things. First, when we went to more complicated system, this is the double vacancy in silicon carbide, meaning more degrees of freedom. Here what we observed numbers, expectation values by doing our minimization below zero. of course, the algorithm should be variational. So the problem is what's going on. And we had to enforce the conservation of the number of particles, meaning the number of electrons by hand through post-processing. So first of all, everybody understand that this is, at the end of the day, not what you will be doing, right? Completely, you need an automatic procedure, you need something better. But at least we understood the problem and we corrected the problem. And when you correct the problem, you restore the variational property of the algorithm, and your numbers are, you converge above the number that you're expecting to converge to. This is one thing. And then the other thing that we did is to do a zero noise extrapolation with so-called split exponentials. And let me just try to give you the concept. So you boost the noise for some portion of the calculation, and then you extrapolate to zero to try to understand whether really you can have, and you have to build the circuits, a convergence. And you do. So we have, so we correct for the number of particles, like shown here, both for the NB center and the double vacancy. We do the extrapolation, and all the technical parts are explained in this paper that just came out 1 or 2 weeks ago. And then we get numbers. So now I will show you numbers that are full CI. This is classical numbers. And these, for us, are exact in the sense of the exact diagonalization of the Hamiltonian. Then I'll show you numbers that we call QC, that are calculation on quantum hardware before extrapolation. And then I tell you what we get for extrapolation. These are energy differences between states labeled using the representation of the groups of these states. And so you can see that if you don't do any extrapolation, you do any mitigation, you get results that are okay. They are not bad, but of course there are errors also that are not negligible. Again, these are electron volt. These are two different ways of extrapolating. Again, they are described here. And you see that when you use mitigation techniques, you start doing better. However, there is a problem that we have not solved, which is here. If you see, these are two degenerate states. And no matter our mitigation, we still have errors that are of the order of 0.08 electron volt. So if you know the results and you just want to know, the trend, this is great. But if you are in front of a problem for which you didn't know at all what you would have to get, this is medium grade. It's not exactly. But anyway, I think that this is progress. This is progress in being able to implement this both, and I want to emphasize this, not only for the ground state, but for the excited states. If you really want to study spin qubit, you do need to have numbers also for the excited states. We understood how to correct results and how to do some extrapolation, and now we have some ideas on how to do a little bit better. So the results here is that we did calculation for realistic systems. There are calculation for models. These are realistic systems on a quantum computer, and specifically the quantum computer is IBM Casablanca. Okay, so what are some of the problems that we are facing? First, we do not have ways, and I mean also the community, it's not only us, to evaluate hard bounds on the performance of the variational algorithm in the presence of noise. We don't know how to do that. So as, of course, everybody understands, even if we get to a polynomial runtime, which I don't know if we get to that, and again, there is a lot of work being done in the community. there could be very large prefactor to the polynomial runtime. And so the way, of course, as we all painfully know, those of us who have, developed algorithm and tried them, one thing is the scaling and the other is the prefactor that can kill you every day because it's huge. And also the large prefactor depends on the circuit that is required for you to build in the gate-based models to realize your Hamiltonian. We are very far from the problem down there of moving data being a roadblock for you, of moving data from classical and quantum computers. But one day, if we really are serious about doing this calculation, I saw you how many calculations we are still doing on classical computers. We will have to move it, right? And so this is something that we have to be aware of. I just showed you the probably simplest and most obvious electronic structure problem, which is one of finding the eigenvalues and eigenvector of a Hamiltonian at t equals 0. And it would be very interesting to go beyond fermionic Hamiltonians. And I'm pointing out here a paper that came out from Fermilab 4 years ago now, where they have a suggestion of how to compute a Hamiltonian electron, photon Hamiltonian on a quantum computer. Okay, so I would like to leave time for discussion, and I would like to acknowledge people who did the work. All the quantum embedding was really started in my group by Ma He. He graduated, now I forget the years. 1 year ago, 6 months, he graduated recently. And then right now, Nan Sheng and Christian Vorwerk, in collaboration with Marco Govoni, who's also here, are working on this. And Benchen Huang is the person who did all the work on the quantum computer. This is our funding. These are our senior collaborators. And I would like to point out that in QNext, which is a hub, quantum information science hub in Chicago, and also in MICOM, we have a number of positions open, and you are very welcome to apply. Thank you very much.